Okay, let's unpack this. Today we're doing a deep dive that goes a layer deeper than the usual machine learning models. We're getting into the foundational engineering.
Right. Data structures and algorithms.
Exactly. The mission is to really look under the hood of that black box and see how the physical organization of data shapes everything.
And you can't start that conversation without talking about the biggest trade-off there is.
Time versus space.
Time versus space. You can't escape it. I mean, think of it like this. Imagine you have a massive library.
Okay.
If you just have a giant, unorganized pile of books, finding one specific title means you have to look at every single book.
That's your linear time, your O of n.
That's O of n. But if you invest some effort and memory, that's the space cost to build a really good index system.
Then you can find it almost instantly.
In logarithmic time, O of log n. And that trade-off, that decision between speed and memory, that drives, well, everything in data science.
So let's talk about the most fundamental building block, the array.
The array, the bedrock.
If I need pure speed, that's my go-to, right? But how does it actually get that famous O of 1, that constant time access? It feels a bit like magic.
It's pure structural engineering. Think of a long row of numbered lockers.
Yeah.
All right next to each other in memory.
Contiguous memory.
Right. And the machine doesn't have to search. It just does a simple calculation. Base address plus the index times the size of each element.
It just jumps straight there.
It jumps, an instantaneous O of 1 calculation. Doesn't matter if you have 10 lockers or 10 million.
And that mathematical jump is exactly why arrays, and of course matrices, are the backbone for libraries like NumPy.
Absolutely. It enables that parallel processing, the vectorization you need for something like, say, linear regression.
But arrays are rigid. What happens when your data is messy and dynamic, constantly changing?
Well, then you need flexibility. And for that, you turn to the linked list.
Ah, the scavenger hunt analogy.
Exactly that, yeah. Each piece of data, each node, is scattered in memory, but it holds a little pointer, a clue to the next one.
So you lose that instant O of 1 access for retrieval.
You do. But what you gain is the ability to insert or delete elements. Anywhere in that chain in O of 1 time is perfect for, data streams or buffers.
Okay, so we have speed and flexibility, but what about organizational logic? How do we build decision-making into the structure itself?
Now you're talking about trees, hierarchical structures.
Their whole purpose is efficiency through elimination, right?
Right. Think of the game 20 questions. That's the perfect way to grasp their O of log n search performance.
You can narrow down 1 million possibilities in what, about 20 steps?
Because you slice the problem space in half with every single question.
Which is the exact principle behind decision trees.
And gradient boosted trees, all those ensemble methods. Each node is just a yes or no feature test, trying to reduce what they call impurity until you get a clear prediction.
So if trees give us logical speed, what if I need the absolute fastest retrieval possible?
Then you bypass all that hierarchy and go straight to hash tables.
We're back to O of 1 again. But it's a different mechanism than the array.
Totally different. Imagine a massive warehouse. You give the system a key, and it performs a little math trick on it, the hash function.
And that function just spits out a coordinate.
Spits out a coordinate, row 5, shelf 12. It's a near instant lookup. Indispensable for things like label encoding when you're turning categorical data into numbers.
Speaking of massive scale, we have to talk about tensors, the engine of deep learning.
A tensor really just generalizes everything we've talked about. Scalar, a vector, a matrix. They're all just simpler tensors.
So a batch of color images isn't just a matrix.
No, it's a 4-tensor. You have an index for the batch, the height, the width, and the color channel. And that structure is what makes vectorization possible.
And vectorization is really the power switch for modern hardware like GPUs.
It is. It lets PyTorch or TensorFlow update thousands of weights at the same time during backpropagation, not one by one.
Okay, last big problem. What about sparsity? The big data issue where your matrix is like 99% zeros.
You can't afford to store all that nothing. It's a huge waste of memory.
So you need a kind of structural cheat code.
Precisely. You use a sparse format, something like CSR compressed sparse row.
And that just stores the important stuff.
It only stores the non-zero values and their coordinates. That efficiency hack is what made huge computations like Google's original PageRank even possible.
So to pull it all together, there's a real synergy here. Arrays and tensors for the raw math, trees for the decision logic, and hash tables for just super fast mapping.
And understanding that synergy is what turns you from someone just applying libraries into someone who can actually engineer a scalable model.
Here's where it gets really interesting.
So researchers are now pushing beyond these traditional sort of static structures like B trees and hash maps. They're experimenting with something called learn data structures.
Which means
It means they're literally using small machine learning models to replace the index itself. The model learns the distribution of the data and predicts the location of a key in memory.
So the tool for organizing the data is itself a product of machine learning.
Exactly. It suggests a future where our fundamental tools of data organization are these recursive self-optimizing systems. Pretty wild idea.
Okay, let's unpack this. You hear the word algorithms just about everywhere, right? Shaping everything from what you see online to how packages find your doorstep. But they often feel really abstract, maybe like a black box. So today, we're going to try and cut through that abstraction. We're going to deconstruct algorithms right from first principles and hopefully reveal just how profoundly they underpin our world.
Absolutely. And at its heart, really, an algorithm is, well, it's a precise set of steps, finite steps, step-by-step instructions, basically, designed to solve a very specific problem or, perform a task.
Like a recipe.
Exactly like a recipe. Think of it as the conceptual blueprint. It's the logical sequence, and it's totally abstract, language agnostic.
Yeah.
It's the pure idea behind the solution before it gets turned into code or anything runnable.
Right, the pure idea. And this blueprint thinking, it's not just for computers, is it? This precise sequential problem solving. It seems pretty fundamental to how we think, too.
Oh, completely. It has defining characteristics, right? Each step has to be unambiguous.
Right.
It needs to finish. That's the finiteness. It takes something in, an input, does something, and gives something back, an output.
And it needs to be general enough to work on different inputs, not just one specific case.
Yeah.
And effective, like actually doable.
Precisely. Think about tying your shoes. That sequence of steps, that's an algorithm. Or a navigation app, finding the best route. Algorithmic thinking is really a core human skill.
Okay, so here's where it gets really interesting for me. The relationship between that abstract algorithm, the idea, and an actual computer program. People often use those terms interchangeably.
They do, and it's a key distinction. The algorithm, again, is that abstract blueprint. The formula, totally language agnostic. A program, that's the concrete implementation. It's taking that algorithm and writing it in, say, Python or Java or C++ on.
Okay, so like the architect's drawing versus the actual house built from it.
Exactly that. The drawing has the logic, the structure. The house is the physical thing built using that logic. The program is where the algorithm lives and runs.
Got it. So how does that logic, that blueprint, actually tell the computer what to do? How does it direct the code?
Well, pretty much every algorithm, no matter how simple or complex, follows this universal pattern. Input, process, output, IPO. You give it data, that's the input.
Right.
It performs a set of instructions on that data. That's the process.
The steps.
The steps, exactly. And then it produces a result.
Simple enough. But how does it handle complexity, choices, repetition?
Well, that's where control flow comes in.
Yeah.
There are basically three fundamental structures. You've got sequential execution, just doing tasks one after another in order.
Okay.
The conditional logic, the if this, then do that, otherwise do something else. That lets it make decisions.
Makes sense.
And finally, iterative structures, loops. Repeating steps over and over, maybe until a condition is met. That's incredibly powerful for processing lots of data or refining results.
And that processing power, especially with iteration, must be why algorithms are so crucial in data science, right? With the sheer amount of data we have now.
Indispensable. Absolutely critical. Algorithms automate these incredibly complex processes on massive data sets, things humans just couldn't do manually, not at that scale or speed. They turn raw, messy data into actual, actionable insights. And they do it with high precision, consistency.
And they enable predictions, right?
Exactly. Predictive capabilities are huge. They let us see patterns, make forecasts. Without algorithms, big data is mostly just noise.
Can you give us some concrete examples? Where are they making a big difference in data science?
Sure. Think about predictive analytics. Forecasting sales for a business, or a bank assessing credit risk for a loan. That's algorithms at work. Or personalized recommendations, when your streaming service suggests a movie you might like.
Yeah, sometimes spookily accurate.
Right, that's algorithms analyzing your past behavior. Also, customer segmentation, grouping customers for targeted marketing, and critical stuff like real-time fraud detection in financial transactions.
Okay, that connects directly to machine learning then. It feels like algorithms aren't just tools for ML. There's something more fundamental.
They are absolutely the bedrock of machine learning, no question. ML at its core is about computers learning from data, finding patterns, and making predictions or decisions without being explicitly programmed for every single scenario. Algorithms provide the structure, the framework for that learning process. They enable the pattern recognition, the optimization like getting better over time, and the ability to generalize to new data.
So machines learn in different ways using different algorithmic structures. What does that landscape look like?
Broadly, there are three main types, three paradigms. First is supervised learning. Here, the algorithm is trained on data that's already labeled. You give it examples of inputs and the corresponding correct output.
Like teaching it, this email is spam, this one isn't.
Exactly. So it's used for classification, like spam filters, or regression, like predicting house prices based on features like size and location.
Okay, supervised. What else?
Second, unsupervised learning. Here, the data is unlabeled. The algorithm has to find patterns and structures on its own. Think clustering, grouping similar items together without being told what the group should be, like finding different segments of customers based purely on their purchasing habits.
Interesting. And the third?
Reinforcement learning. This one's different again. The algorithm learns by doing, by interacting with an environment. It tries actions, gets feedback in the form of rewards or penalties, and learns strategies to maximize its rewards over time.
Ah, like how AI learns to play complex games or how self-driving cars learn to navigate.
Precisely. Autonomous systems often rely heavily on reinforcement learning.
Wow, okay, so you've got supervised, unsupervised reinforcement, and presumably many specific algorithms within each. How does anyone choose the right one?
Yeah, that raises a really important question. The truth is, there's no single best algorithm. It's not like there's one magic bullet. The choice depends heavily on the specific problem. Are you classifying something? Predicting a value? Finding groups?
Right.
It also depends on your data. How much do you have? Is it ladled? Is it messy? And what do you need from the output? Just accuracy. Or do you need to understand why the algorithm made a certain decision? Interpretability.
So it's more art than science sometimes.
There's definitely an element of craft to it, yes. Understand the strengths, the weaknesses, the assumptions of each algorithm. It's often an iterative process. Try one, see how it does, maybe try another. The art of algorithmic craftsmanship, you could say.
Okay, so pulling this all together, algorithms are these fundamental, precise sets of instructions. They're beneath almost all computational problem solving today. They really are the logical architecture of our digital world, enabling all this amazing automation and prediction we see.
That's a great way to put it. And what's fascinating here, I think, as these algorithms become more and more woven into the fabric of society, making decisions in finance, healthcare, even justice, understanding their principles, how they work, what their limits are, where potential biases might creep in, that stops being just a technical issue. It really becomes an ethical imperative, doesn't it, for everyone? We need to ensure they're used responsibly beneficial.
That is a crucial point. Understanding the blueprint is key to shaping the house responsibly. A really profound thought to leave everyone with. Definitely keep pondering the algorithms, visible and invisible, that shape your world.